All right.
Did you send that for?
I will begin with a word of prayer. So, Dear Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you just bless our work today. Help us to glorify you, what we do. And just help us to learn a little bit more about your creation as we prepare for the in-class exercise on Friday, Lord. In your name I pray, Lord Jesus. Amen. As you guys know, as you guys may know, the test in physics, well, really in any class, the test is the highest form of class participation. You know, like, it's, anyway. So I have your mission 6 here, and I'll just hand a few of these out. Find anybody. Oh, there you are. Where'd Simon go? Oh, there you are. Haley? Katie? Cameron? Megan? Sophie? Sarah? Trenton? Jeremiah? Noah?
Last name? I think it's right. Yeah.
Justin? So if you're my calculus 2, I already gave these to you this morning, right? Gideon? Oliver? And while I'm doing this, if you guys would pass in your mission, that would be good. Oliver?
Thank you.
Caden? Jeff? William? Michael? Michael? Harley? Ben? Marshall? Okay. I have now sent your name on YouTube. I'm sorry. If you'd like me to, I can delete this.
No, that's okay. That's
okay. All right. That's good. Let's see. your work rhymes are what? So you're Thomas. Brian. Matthew. Danny. Sorry. All right. All right, do I have everybody's mission 7?
I got basically.
Thank you, thank you.
So I'm not sure my work.
You're going to put missions 5 and 6 on campus.
They're not there?
No, sir. At least not that I can see.
That's weird.
Yeah.
I thought I did that. That's not good. I have everybody's mission 7?
I wasn't here when you handed out mission 5 last week.
Well.
Either that, or we just haven't gotten the attendance sheet.
All right, do I have everybody's mission 7? Okay. Landon? This is just, that's 6.
These are mission 7.
Mission 7, okay, thanks. So you guys were saying that I have not posted the solution to mission 5 or 6 in Canvas? Oh, well, who cares about that? I mean, I have them. I just have, I will put the numbers in. Is that matters?
Yes.
What happens if I don't put the numbers in?
I saw.
It's upsetting? Oh, okay. I mean, I will put them in at some point. Best case scenario is I lose that paper, at which point everyone gets a 24, right? But you're like, well, I already have a 24. I want the other people who didn't get the 24 to not get a 24 like I did. Well, if that's how you feel, then, well, that's, I guess you're a bad person. I don't know, but no. No, I will put those numbers in. I just haven't got to it. All right, so any other questions? My laptop is still shedding. Yep.
Is the attendance sheet being passed around?
The attendance sheet is right here. Thank you. Did I pass it around last time? No. What was the date last time? Thank you for your pencil. The 20th? So that would make today the 22nd, right? This is a twofer. As you can see, I have reverted to an old attendance sheet. It's okay though. According to what frame? All right, so guys, I don't have a scan of the Mission 7 solution yet. I have it solved. I just don't have a scan of it. $22.66. The top hat is $22.66. Sorry I didn't top hat in calculus this morning. Don't worry, we'll do it twice tomorrow to make up. So, listen guys, I have to apologize for Mission 7 because I have done something dumb. Something very, very dumb. And that was when I wrote problems 80 and 81. In my mind, I was writing 0.99 C. What I wrote on your paper was C divided by 99. These are very different. C divided by 99 gives you a gamma, which is 1.0, well, uno momento.
It's like 99 divided by square root.
It gives you 1.000051019, assuming you're using 3 times 10 to, assuming you're using 3 times 10 to the 8th as the speed of light, right? I mean, technically, what is the speed of light actually? 2 point what? 2.99742? Is that right? 2.998. See, I was remembering 2.98, but I could be wrong. I'm probably wrong. So if you did that, that would change it a little bit too, maybe, right? Anyway, I'm going to tell the grader to like take it easy on you for problems 80 and 81 because unfortunately with my choice of velocity, you end up, in order to calculate these things meaningfully, you're taking the difference of numbers where there are interesting things happening over about like 12 or 13 digits. Your calculator can't do that. I mean, you can do it in Wolfram Alpha, but you cannot do it on a calculator. So that's not what I was trying to test, right? How do I avoid this? Well, if I ask this questions on the test, instead of doing C over 99, I would do, you know, like 0.99 times C, in which case that'll give you a gamma, which is like pretty big, right? And then the calculator will be happy and everything will be fine and dandy. So sorry about that. That's what made the problems seem like way harder than they actually are. It's just my poor choice in velocity. So sorry about that. Do you guys have any questions about anything? Yep.
Are we gonna have to draw like space-time diagrams like we did in 83?
Yeah, I don't think I'll put a space-time diagram on the test. I can give that to you. Or did you want it?
No.
Okay. See, my usual approach is when somebody asks a question like this is, well, sure, I can put that on the test. Anyway, so what's the next question? Yep.
Kind of along with that, will the verbal explanations, like the first 3 on the front of the mission, be on the test too? Like, or is that also just understanding and like?
I think that the first 3 questions are probably more reasonable than the later questions in terms of testing, because these things I've actually spent a lot of time on as compared to the later ones, right? but I'm always very generous. Like if you misspell Michelson or misspell Morley, I'm not like, oh, it doesn't count, you know. So yes, but I wouldn't spend a lot of time and energy on that either. I mean, you can read the answer. I'm going to post the solution, right? And you can look at that and decide for yourself if you're close or not. Like, for example, my solution to problem 75, I tell you that g mu nu is 8 pi g t mu nu. This you do not have to know. This is just a comment from me to you. That's the sort of analog of Newton's second law for general relativity. So, and obviously, you know, the things I said about cosmology last time, like I don't expect you to remember those verbatim. That would be unfriendly, you know. I might pick like a token kind of like big theme of that conversation and ask like a token question, but it wouldn't be worth a lot. It'd be like, you know, a point or something stupid. So, because sometimes I'm just curious, like what of what I said actually stuck. Was it so abstract and so out there that it didn't have meaning to you guys, or did that actually stick for some of you? I mean, I'm always curious about that, but that's not so much about. That's more just a vain curiosity of mine as opposed to like testing whether or not you understand physics too, right? So I wouldn't worry too much about that. I'd worry much more about, can I solve a collision problem, you know? On that note, so yeah, if you have not got back missions 5 or 6, you have to come with me to my office after class. We'll find it there. It's in my big binder there, I think, most likely. And on that note, we still haven't graded the problem that I gave you unfriendly circular advice on, the inclined angle problem. So if you'd like to turn that in at the start of the test, I'll collect those and like grade those separately, just because I think you should get something for it if you've done it. And a couple of you have done it, but I've not given you credit for it. So if you're such a person, you can turn it in again. And I will, of course, be understanding if somehow that has gotten, like it may be exactly what we're talking about with Simon, because I think, Simon, you did that problem, and I think it's on your mission 5, maybe. Yes, sir. So like, I want to get that back to you so you can turn it back to me. Like you can just rip off that last problem and turn it in at the start of the test. So if you haven't...
I did do it on that mission.
So right.
Just grade it right now.
No, I haven't. No, I'm going to collect all of them at the start of the... So like I will... Because I've given them back to people, so what I'm saying is it hasn't been graded. So just tear off that last page. If you haven't done it already, you can try to do it and turn it in. If you've already done it, just turn it in. And I'll collect it at the start of the test and give you some, you know, it'll be worth maybe 5 points if you've done it. Yeah. Yeah, question?
Yeah, that was my question.
How much? Oh yeah, 5 points. For those of you who are in calculus 2, have you noticed that there's like a 10-point bonus problem in the notes that I wrote up? Guess not. So anyway. Oh, I also have some good news that is also bad news. So the good news is that I'm teaching calculus 3 next semester, I think. The bad news is I'm not teaching physics 2, I think. Now, this is going to be more certain once Dr. Joseph sets the schedule, maybe tomorrow. The schedule's already set, right? But there's not names attached to things. Names should appear soonish if you're waiting. Because some of you have asked me about that, so I don't think I'm teaching physics in the fall. Unless I do physics in Calc 3, which, you know me, I'm going to do it a little bit. It's in my nature, but not that much. Right? Do I ever test on the physics in calculus? Not really, right? Oh, that's not true. I do ask velocity acceleration problems, don't I? My bad. Other questions? Let's see here. If I can get out of this. Let me out. Oh, yes, question.
Are we gonna have to do like conversions in the test? I was looking at the problems last time you suggested on mission 4, and there's one where you have to like convert like horsepower to watts.
Oh, yeah, I would not ask you to convert horsepower to watts. No. No, no. If I had spent 5 minutes of class doing it at some point, sure. But, you know, short of you asking me that question, I forgot there's such a thing as a horsepower. But I mean, I suppose that's interesting, right? You talk about cars having 700 horsepower. What does that mean in terms of watts?
Whatever 700 times 745.7.
745.7? Is that right? Whoa. Whoa, whoa. Let's be a little bit less ambitious. What is 200 horsepower in terms of watts?
1491.
No. The number. What was the number? You had the conversion. How many horsepower is a watt? How many watts in a horsepower?
745.7.
745.7. Now you're making me want to do this on the test, man. This is interesting. Holy moly. 149,140 watts. Dang.
Tell us the conversion factor.
So, have you guys looked into the e-scooters? I've spent too much time looking at e-scooters over break, and like you can buy an e-scooter with like 7,000 watts. Do you know this? That sounds really impressive until you take 7,000 and you divide by 745 point, what was it? 7. This is 9.4 horsepower. Big deal, right? Well, but what's the difference, of course? The electric motors, like that linear torque, yeah, it's not the same, is it? But the power curve. Yeah, you can get a scooter that you can go like 70 miles an hour on. You know that? For a couple weeks before you die, I guess. But you know.
Hit a pebble.
You guys talk about racing wheelchairs?
Yes. Would you help the team? Would you help the team?
You need a faculty sponsor for your wheelchair race league?
Theoretically speaking, of course.
I would sponsor that.
Yes. Dude, wait a second.
I would sponsor that. Sure, why not? I mean,
I think we make it like a nationwide thing. I want Liberty University to face of wheelchair racing.
Liberty to be the face of wheelchair racing. These are powered though, right? To be clear, wait. Wait a minute. We're talking about powered wheelchairs, right?
Whatever your imagination creates.
Because if we're just talking about like people of their own volition pushing them, I'm not interested in that. That's got, you know, that would require actual skill and stuff. I'm just interested in like, you know, throwing a motor onto a wheelchair and seeing how fast an idiot can go around in it. I am fascinated by the folks who like play basketball in a wheelchair. All right. Cohort. I heard the phrase cohort of Barbie cars. All right. I'd say settle down. Well, I'm torn. Like on the one hand, I want to say settle down. On the other hand, I want to read you my most recent batch of Peter jokes, but I can't do it because the calculus has already heard it, so they know the answers. They're going to ruin it. You're going to be quiet? But shouldn't we be preparing for this test? No? All right, well.
We can push the test back.
Push the test.
The answers are up.
Ah, look away. It's hideous. All right. Okay.
Test back to Monday.
I will not be moving the test back to Monday. Unless there's a blizzard, in which case, sure. So, what's the temperature Friday? 80. Yeah, so if you can, if there's even an inch of snow, the test is moved back to Monday. How about that? I'd say a dusting, even natural snow falling from the sky, not produced by any kind of engineer in some sort of last ditch attempt to get out of the test. Question number 1. What do mountains use to stay warm? Yep. Very good. Where can you buy a rainforest? Where you read it? How fast do you read? Let's find out. Where can you buy a rainforest? Oh, you guys read. Why did a lettuce beat a carrot in the race? Why did the lettuce beat a carrot in the race? It was ahead. These are horrible. I like this one. What did the snowman say to the other snowman? He said, "Do you smell carrots?" Actually, can you smell your own nose? I don't know. What's the best Mexican food to eat in the winter?
Burrito. Very
good. It is burritos. You read it? Oh man, I thought you had internalized the mind of the Actually, I feel strongly that these were not written by Peter. These reek of a joke book. These are adult puns. These are not the mind of a 10-year-old. These are not the same as the other ones. I don't believe these are Peter originals. I'm going to have to confront Peter about this. He should be citing his sources. Yes?
How certain are you that he's not looking up at the
I'm pretty sure. I mean, he said it's a Peter original, so I trust him. All right. Let us talk about physics. After all, oh, come on. Oh, that's true. Go figure. You can do it. You can do it. All right. Some thoughts. Work energy theorem. You should know it. What does the work energy theorem say? It says that the change in kinetic energy is equal to the work done by what? The force. Which force? We have to be talking about the net force. All right? That's important. Work energy theorem is only for the net force. And so that's essentially what's going on here. Is the net force is this pushing force, and so the work done by the net force is equal to the change in kinetic energy, and so that's how I can solve this problem. Now you might say, hold on a second, that's not the net force, there's also 2 other forces involved, and you'd be right. What are the other 2 forces? The normal force and gravity. I'm assuming no friction, right? Well, essentially frictionless, yeah. So the thing is, the normal force and gravity, they don't contribute to the net force, right? They cancel out. So the net force is actually equal to F sub 0 in this case. Now, what's a conservative force? This is something you should be prepared for. What did we say a conservative force was? It's a force for which there exists a potential function, right? It means you can write F is equal to minus the gradient of a potential function. You were here, we talked about these things. I remember it. I know it was like forever ago. But those things matter for the test, right? So let me show you one. Come on. Well, is that the previous mission? Am I on the wrong mission? Is mission 4 also relevant?
Yeah.
Yeah, I should start with mission 4. Now, some of you were like pretty lost when we were doing these things to start with. You need to go back and look at it again now that you've had a few weeks for it to settle. It's not hard. It really isn't. Okay, so, if there's an issue like this on the test, you got to come and talk to me about it so we can settle that kind of thing, all right? If you're not sure about the meaning of words, in terms of is it left, is it right versus up and down, like that kind of thing, yeah, just talk to me. I'll help you. All right, we'll pick a direction if I, for some reason, make something ambiguous like that. This force is one-dimensional, A minus kx. And so to find the potential energy, I have to integrate minus du dx. And when I do that, I get 1/2 kx squared minus ax plus c. But I said that we want the potential energy to be 0 at 0, so that makes the constant be 0, and there you go. Now once you know that, you can calculate the work done by calculating minus the change in potential energy, right? So when is this true? When is the work done minus the change in the potential energy? Well, that's true when the net force is conservative. That's when this is true. So if your net force is conservative, you have work done by the net force is equal to two things. It's equal to the change in kinetic energy, and it's also equal to minus the change in the potential energy. You put those two things together, you get that energy is conserved. All right? Energy is conserved when the net force is conservative. I would encourage you to go back and look at these. If you didn't understand it before, all that's really done is you plug in the parameterizations for the curve, and you take the dot product with the velocity, and then you integrate this thing here. The meaning of this is it's the power per, it's the power at time t. So you integrate the power to get the net work done, right? In other words, force dot the velocity is the power. That's how we're defining work. You integrate the power over time. That's really what the definition is when you sort through it. In that case, we learned F is not path independent since the work done in two different paths was not equal, right? We had characterizations of conservative forces. What did we say? We said force is conservative over some region if either you can find a potential energy function for it, such that minus the gradient of the potential energy is the force. That was the definition. Or the integral along two coterminal paths in the region. In other words, two paths which start and end at the same point. That the work done on those two different paths is equal no matter which pair of paths you take. That's path independence. Or the other way to do it is that the integral around any loop in the space is 0. These are equivalent characterizations of a conservative force. And then, of course, we looked at some problems where you find the potential energy function, right? I hope you can do these. All right? How do you check? Well, you need to check by calculating the gradient of your answer, right? Which is the x derivative, comma the y derivative, comma the z derivative, if they're in 3 dimensions. And if it works, you should get back where you started. Of course, you also have to multiply by the minus. Watch out for that. But you guys do have a 3x5-inch card you can bring, right? So one of the things I would have on my 3x5-inch card if I was you is this force is equal to minus the gradient, right? And I would remind myself what this funny looking triangle upside down with a u means. It just means this vector of partial derivatives, right? Any questions? Let's see here if there's anything else I want to hit on here right the moment. Oh, these problems are nice. These problems are very conceptual, and they don't really require a lot of mental effort on your part if you understand it. So these are nice test questions, this kind of thing. See, because you either understand this and you can do the problem, or you don't. You're not going to waste 30 minutes on this problem and in some sort of unfortunate way, like some other problems I might think of. So the idea is simply this. If you're given the potential energy diagram, right? If you want to see what motions are possible, you have to have the net energy is larger than the potential energy, right? Because total energy is potential energy plus kinetic energy, and kinetic energy is positive. Why? Because it's 1/2 mv squared, right? So for us, mass is what? Positive, right? We don't allow for negative mass. Apparently there was some dude who was looking at negative mass in the early 70s or late 60s, Herman Bondi or something. I was watching some video on YouTube about it yesterday. It was interesting. But anyway. You guys ever watch any of the videos from Weinstein? No? You know what I'm talking about? No? Okay. Cool. There's it's a long story. The student I work with, he says he's kind of a shaman. That's a kind of a good description for this guy. I'm just waiting for him to start selling me essential oils or something. Oh, I'm sorry. How are you guys on the essential oils? My brother and I like to say that the most essential oil of all is petroleum. So, I'm a horrible son. But anyway, so the point is, you draw the energy diagram, you draw the energy level, you have to have the energy curve is above where the potential energy is. So like, if my energy level is here, if it's 1 joule, then I can only have this motion classically, all right? Anywhere else, the motion is, you know, forbidden by energy analysis. So that's, I mean, I hope you can understand this problem, yeah.
Conceptually,
Mhm.
suppose that the total energy was 1 joule, and
Mhm.
then somehow the particle was placed at x equals 20 meters. What would happen?
Oh, then we would definitely be in the context of quantum mechanics, and then it would tunnel back to like where it was physically, classically allowed. Something like that. So like quantum mechanics allows you to tunnel through into the places which are classically forbidden. So to flip that around, I would assume if you're where you're not allowed to be classically, that's a quantum mechanical situation, so surely you must go back to what's classically allowed. I think what would be physically real, what would be physically, I would think of it like this: the potential would essentially pinch you back to where you're supposed to be, kind of like that, something like that. I guess if you materialize inside a wall, I would much prefer the situation that you get pushed back out, so as opposed to like what usually happens in sci-fi shows when you materialize inside a wall, which is what? You just get stuck there, and you know, some part of you is comically like sticking out, so you know, something like that. Let's see here. So obviously if I ask a graphing question, it's got to be based on graphing you can do, which is polynomials, right? Maybe sine, cosine, I suppose. Let's see here. All right, anyway, I guess that's enough about that. I don't know, are there any other questions? I mean, I can't talk about everything here in 20 minutes, but yep.
Is the sample test you posted on your website from 2012 an accurate representation of each year that we covered by this test?
That is a fantastic question. I do not know. Was that test 2?
Yes, sir.
Oh man, stupid finger. Let's see here. So you're saying I should just use this test again? I don't see anything here which wouldn't be reasonable for the test, but it's not quite everything we've covered.
Because I don't think there's special relativity.
Yeah, so there should be a token, couple of special relativity questions on there. And, but yeah, this is pretty much ballpark. Yeah. Maybe we should look at this. But I will do what I usually try to do, which is to look back over the missions that I've assigned you guys, right? And try to think about what should you have learned from doing those problems as I make your test, you know. This test might be missing the more mathematical version of the work calculation that might be missing here, because some semesters I cover that less or more. But let's see here. Essentially, massless spring is attached to 2 kilogram mass. It's allowed to oscillate without friction on a horizontal one-dimensional motion. Suppose the stiffness of the spring is k equals 10 newtons per meter. At t equal to 0, the mass has a speed of 1.2 meters per second. As the spring is stretching out a distance of 0.2 meters from its equilibrium, then what is the maximum distance that the spring stretches from equilibrium? So yeah, this is just straight energy conservation. So you have the kinetic energy plus the potential energy of the spring is constant throughout the motion, and so you can compare the initial energy to the max stretching, right? And so the place where the spring is maximally extended is where right before it turns back around, right? So that's where the velocity is 0. So that's why I set 1/2 kx max squared equal to the total energy, because that's the instant when it's at maximally extended. Does that make sense? Yep.
On the last test as well, there was that last problem at the end, which was kind of that weird proof problem that you ended up like not counting as part of the test and then re-offering as bonus points. Will there be that kind of problem at the end of this test as well?
I would like to think that the problem on the test will be able to be achieved during the testing time. Like, that is my dream in the bonus question, is for the bonus question to happen during the time constraints of the test. But there's a precedent for that happening. Let's hope it doesn't.
But will there be like a proof problem?
There should be something harder on the test, whether that's a proof or whatever, but yeah. So, let's see here. This one, how about this one? 82 kilogram running back, 5 meters per second, collides with 110 kilogram linebacker who's initially at rest. What's the resulting velocity of the football players? So here we just conserve momentum, right? The initial momentum is the 82 kilograms times 5 meters per second. And the final momentum is they're stuck together, so the net mass is this, right? Times the final velocity, and so there it is. Like, this is pretty easy, I think. Hopefully everybody got that question on that test. I don't know, it's been a few years. I know what happened to them. 2012. They probably got kids. I was like serving in Awana with somebody, and like I had their kid in Awana, and all of a sudden he referred to me as Dr. Cook, and I was like, whoa, wait a minute. Oh, he was my student from like 5 years before. It's like, because you guys look different 5 years from now, most of you, I look more or less the same. You can just look for the blue shirt, right? But anyway, what I was going to try to say is I will try my best to make the problems on the test understandable without like a lot of, assumptions. Like I try to make the problems on the test clear. Like we had one problem in the homework about a ninja running off a bridge. If that problem is on the test, it should come with a picture so that you have a better sense of what I'm talking about, right? So if on the test, is he reading something you have no idea what I mean geometrically, just come, ask me, could you make a picture for that problem? And then I will make a picture on the board for you, and then we'll all be happier, all right? You have not because you ask not. So ask. How do you calculate the average force? Remember, the average force you can get from the impulse divided by the time, change in time, right? So like the F average is the impulse, the change in momentum, and divided by the change in time. This is useful for like you're kicking a soccer ball, or you can calculate the average force the wall puts on a ball that's rebounding. So let's see here. Center of mass. I mean, if I ask you to find the center of mass, if I give you the masses and the locations, this is just kind of a brain dead problem. To make this problem interesting, I tell you where the center of mass is, and I ask you where one of the masses is. Then it becomes a problem of algebra, which is more fun. But then I'd have to give you more than like 1.5 inches to work it. Let's see here. What's an elastic collision? Something more basic. What is momentum? Yeah. Yes, but if I had to ask you, like, What kind of object is it, though? Is it the same as energy? What's the difference between, say, energy and momentum? Energy is a scalar. Momentum is generally a vector. So if you're solving a problem with momentum, unless it's a one-dimensional problem, in one dimensions we can get away with using scalars for vectors, right? We just use plus or minus to indicate direction. But in two or three dimensions, if you're working a momentum problem, you have to think in vectors. If you don't, you'll be wrong. It's just inevitable, all right? So that's just a comment. I mean, it's hard to miss that, but it nevertheless escapes a lot of students in this part of the course. Like, there's always a subset, like 30, 40% of physics who doesn't quite get they have to do momentum with vectors. Now, if you're not that person, you probably wonder how that person could be that way, but it happens. They're among you. Let's see here. Didn't mean to dehumanize the students, my bad. Sorry. Of course, I want all of you to, make excellent score on this test, and I hope you understand. If you don't understand something, come talk to me about it or something. But anyway, I think that's all I have to say for today, partly because I'm out of memory on my video card. So, am I out yet? How many minutes do I have?
It looks like 2 minutes.
2 minutes? I got 2 more minutes. Any questions? I think we can stop it here, and then if you guys have questions individually, you can come talk to me. So, all right? You stop that. All right.
Now zoom in, where's the slow?